BIM, I suppose, has evolved from its first use in the maritime industry to use in the manufacturing facilities and more recently the commercial construction sector. There remains legacy issues that BIM must overcome in the commercial sector if it is to achieve the same level of success that it has in the industrial sector. Current work practices such as issuing of drawings, knowing what drawings are current and identifying changes to previous revisions are not as regimented in the commercial sector as they would be in the industrial sector. And this is a difficulty going forward that must be addressed if costs are to be controlled. BIM processes are more labour intensive than conventional 2D design, and as such any changes that occur during project development must be controlled and approved in a holistic manner to ensure that team members do not incur high labour costs, and indeed clients can have a basis for approving or rejecting claims for additional fees associated with redesign. My experience in the commercial and industrial sector has taught me that BIM can be used on all projects in some form or fashion, but it is not necessary to model the complete installation of a project in order to achieve success. The focus on clash detection to minimise construction costs can encourage parties to overuse BIM in areas where it is not required. Specific areas that would require 3D modelling would be highly congested zones such as service risers, ceiling voids and plant rooms. There is no real benefit to be had for consultants in creating an entire 3D model of a building's systems unless they are going to be paid for their work. Clash detection is the primary reason behind the growth of BIM, but additional benefits such as material estimation can also be carried out using a model. It is important that consultants clarify the need for this with their client at the outset, and as going to this level of detail is more time intensive than conventional modelling and would result in project milestones being missed if hours required are not estimated. The evolution of the internet and access to more data online has resulted in more information that can be utilised by BIM software. This greatly enhances a consultant's ability to assess the environmental performance of a building at concept stage using mass models in conjunction with site-specific weather data to give preliminary results in relation to building energy usage, renewable energy potential, environmental performance and running costs. This gives clients and architects more sound footing when appraising scheme proposals and will no doubt result in better, more efficient buildings. This workshop will look at the various products for detailed analysis of project energy performance and compliance with building regulations, and particularly the workflows of using design data that has already been created to allow for earlier analysis and problem finding to facilitate quicker design decisions and more sustainable building. Varming Consulting Engineers were founded in 1946 with Irish offices located in Dublin, Cork and Roscommon, and are one of the leading dedicated M&E building services consulting firms in Ireland. Specialist skills are tailored to suit clients' diverse requirements in all areas of the construction market, such as healthcare, education, retail, commercial, industry, leisure and tourism. They have grown within a culture based on a tradition of innovation and continuous learning, allied to the use of promotion of both existing and emerging technologies, which has resulted in numerous award-winning projects throughout their history. They can draw on a wealth of international experience and resources to deliver quality projects through the Varming International Alliance, which consists of Irish offices merged with offices in London, Edinburgh, Sydney, Canberra and Copenhagen. Our speakers this morning are John Purcell and Declan Alcock. John Purcell is a chartered engineer and is currently chairman of Varming Consulting Engineers. He joined Varming Consulting Engineers as a graduate of UCD and during his long career has served the company at all levels. John's initial involvement in engineering construction was in the design of pharmaceutical manufacturing facilities, in which he had to address the creation of sterile environments. In recent years, this knowledge was readily transferred to clean room design for electronic application and for laminar airflow systems for healthcare operating theatres. John is a past SIBSE chairman and also a silver medal winner for his services to the industry. Declan Alcock is a senior sustainability engineer with Varming Consulting Engineers with 14 years experience in building services consultancy over a range of educational, healthcare, commercial and residential projects. 9 years of this experience has been focused on sustainable building design and building performance simulation. Declan holds an MSc in Energy and Sustainable Building Design and has performed advanced simulation analysis on in excess of 150 projects with particular expertise in dynamic thermal simulation, computational fluid dynamics, climate and daylight analysis, airflow modelling, occupancy comfort, and adapting buildings to climate change. Without further ado, I'll hand you over to our first speaker, John Purcell.
Good morning, everybody. Thank you, Keith, for that introduction, and thank you to CIBSE for being the event partner today. I'd also like to thank Alan and CITA for inviting Varming to make this presentation. The subject of our presentation is project analysis, by which we mean, for the purposes of today's talk, building performance analysis. And Declan will be addressing BPA both from within and outside a BIM environment. Keith has told you about Varming, but Varming is a strange name, and we believe that our company has an interesting history. And I'd like to share just that very briefly with you before we get ahead with our presentation proper. What we do, as Keith has mentioned, we operate from both Dublin, Cork and Roscommon. This is a slide that we use many times in our history one, and it relates really to the arrival of Varming in Ireland. And the post-war years right across Europe saw a revival of construction activity and created, are we jumping on here? Sorry. It created the opportunity for the introduction to Ireland of two unfamiliar sounding Danish surnames, Arup and Varming. And the engineering consultancies founded by these two Danish engineers in the 1940s continue to operate today under the same names. The catalyst and prime mover was the Irish architect Michael Scott, and his hospitality, Irish hospitality was always famous, and his hospitality extended to making available office space in his building in Merrion Square to these two practices, and they operated from those offices for several years. And like so many projects today, the first client was the Irish Transport Company, a state company, and the first most notable building was the Bus Áras, which is opposite the Custom House and is an iconic building in its own right. This is Varming performing with his cello in front of the Opera House. He was a very strange, very special man. His father was a prominent Danish architect. I don't know why we seem to be on a anyway. His father was a prominent architect. His mother was a musician, and when he founded his practice in 1933 in Copenhagen, he adopted a design philosophy reflecting his particular interest in the relationship between architecture and engineering, and his approach to the integration of building services with building architecture, and his pursuit of comfort, light and colour struck a chord with many architects and clients. And I have no doubt that if he were here today, he would be a very strong proponent for the adoption of BIM as a key step on the way to unlocking the barriers to the full integration of engineering with architecture that he always followed. Keith has mentioned the Alliance. The Alliance this year celebrates 80 years of its founding in Copenhagen in 1933. And over that period, the Varming name has been associated with many major iconic and landmark buildings, where the operation of sophisticated building services installations are of critical importance. And in all of his practices, he promoted the concept that his Varming engineers should maintain a tradition of design excellence inspired by a spirit of innovation. And you can see that some of these buildings, major large buildings, but there's quite a range of buildings. The only two Irish buildings we're showing there are government buildings and Tala Hospital to show the range. But as you can imagine, over some 65 years, we've quite a portfolio here in Ireland alone. So back to the purpose of our meeting here this morning. And hopefully you all recognise the programme of the CITA Technology Series talks for 2013. And we've already had three talks on programming, excellent presentations on programming, conceptual design and detailed design, and all of them in their own way focused on BIM. The title of our talk, as Keith has mentioned already, is Project Analysis. And project analysis has a different focus in that we are going to look at building performance analysis as the central theme, but it will be presented in the context and in the arena of BIM. Now, there are many M&E designers operating in Ireland today, and some of them here this morning are online, who are performing a range of different building performance related design analysis. And these include computational fluid dynamics, energy consumption, and building regulation compliance. All of these are part of the building design process, and this slide, again, one you'll be familiar with, you'll have seen it before, is being presented to show that currently there's a divide, there's a huge activity in the whole BIM environment. And as we move into the dynamic simulation modelling, a lot of the software that has been in use and is most commonly used is outside of BIM. And the challenge that we all face is that by the time the information emerges at the analysis stage, it's too late to influence the initial design. And what we're going to try and describe and explore with you this morning is how we can move that forward, or what opportunities exist to move it forward. So much of what Declan has to say will focus on that. I'm putting up this chart, and you've all seen this chart many times, but it's only really to highlight once again this is the effect, cost and effort graph, and the black line, number 3, is really a workflow which focuses on drafting, and that's what we have at present. But as you can see, when we set that on a timeline against the ability to impact cost and performance, which is the blue line coming down, and the red line of making design changes, it's obvious that the advantages that can be achieved if we can move what we have called by the green line, which is the BIM workflow. And that's very much the issue that we're going to try and address today. Declan has quite a long presentation, so at this stage I'm going to hand over to Declan and invite him to come forward to continue with the building performance analysis. So thank you very much.
Thanks very much and good morning. This first slide is basically just an overview of building performance analysis and I suppose the headline areas of it. It's basically involved with the investigation of the performance of a building in terms of its energy and carbon. And this in turn can feed into life cycle costing and help us to prioritise investments. And it looks at building regulation compliance. In addition, it's about the investigation of the comfort of occupants in terms of the thermal and visual environment. The issue with the design process is, by nature, it's an iterative process. That's a bit of a mouthful this time in the morning. But as it goes along, room functions, geometry, fabric will all change. And this in turn has implications for building performance modelling. Simulation modelling as well, by its nature, is time consuming. There's a lot of manual input of data before you actually get to the analysis stage. And as the design progresses, the model must follow that changes to the architect's layouts. The implications for this is we have to re-simulate the model, rebuild geometry. There's a lot of exporting results to Excel or Word to interrogate results and report on it. And this leads to a significant proportion of the fee being expended at just model preparation rather than detailed analysis. So the dilemma for us usually is at what stage you actually commit to building a simulation model to reduce waste of time and duplication of effort. So in attempting to seek alternative solutions to that dilemma, as with BIM implementation, the idea is to identify areas where the workflow isn't efficient and try and bring in options to make it a more efficient and streamlined workflow. So our question is BIM-based analysis the answer to that? So as you can see, there's a huge range of software packages on the market from all the major vendors. For the purposes of today, we're going to talk about IES Virtual Environment, which the IES, we use VE Pro for the majority of our analysis. That's in turn their range of products. They have scaled down versions of that, since, like Gaia, Ware, IES toolkits, and there's a plug-in for Revit as well. We're also going to be looking briefly at Vasari. Okay, the reason why we use the virtual environment, or VE Pro, for the majority of our work is because we have knowledge and confidence in its use. We've total control over the inputs. It doesn't rely on default data. You can basically set up the inputs whatever way you prefer to do it. And as it's taught in third level colleges, students are coming online, going into the market with a knowledge and understanding of it already. For early stage analysis, as I said, we're going to speak about Vasari slightly, but the choice of software really depends on the level of accuracy that you want, the stage of the project, and what type of outputs you require for reporting purposes. This is just an example of where preliminary design and detailed design can be used in conjunction with each other. On the top left-hand corner there, it's a shading study to investigate the extent of solar radiation or the possibility of it on different facades of a building. This in turn can lead to glare issues. And on the bottom right-hand corner, it's an iterative process to design or to investigate various glazing options on a facade, so we can maximize the quality and quantity of daylight without compromising on glare and solar heat gains. The next few slides are going to be based around dynamic simulation modeling with the virtual environment. And what it does really is it takes a holistic approach to building performance analysis. It looks at all the passive and active systems, as you can see there, how they integrate with each other and with the fabric of the building, and how the climate influences that. It gives us detailed climate data. It's at hourly intervals rather than monthly averages. And you can get a reporting of your data like every 6 minutes. So you can really interrogate the details and results the results in detail, and this in turn can inform facilities management and investment priorities. The top right-hand corner, it's a very simple graph, but it's an example of natural ventilation flow rate and external wind speed. That's just taken over a day, but you can see that you can cut it down into small chunks and investigate it in detail. The second one is particularly useful in the likes of school design. Building Bulletin 101 is used extensively in the UK, which sets pretty stringent criteria for ventilation flow rates, carbon concentration, and overheating requirements. And this level of detail is really where the likes of VE Pro comes into its own. So this slide is just really an example of the types of outputs we can get from it. And as I said, it's a holistic approach. It doesn't take one aspect by itself. It looks at how everything integrates with each other. For example, you have visualization of light, daylight analysis, which it's not just about daylight factors, it also looks at diversity, uniformity, distribution of light. Shading analysis, over here you have overheating, carbon concentration as well, and solar gains during the day. Some basic visualization, building regulations compliance, and computational fluid dynamics, which is about looking at airflow and heat transfer processes within a space. That's particularly useful for occupant comfort and areas of high equipment games such as ICT rooms, which is what that image is taken from. So as a case study really of our typical or traditional workflow, we're going to take the proposed redevelopment of National Concert Hall. Now, like a lot of PPP projects, this never went ahead, but there was a huge amount of effort, time and money put into actually getting the design together. So I hope to sort of illustrate with this how that effort, time, and can be dragged forward through using BIM tools rather than going through this whole detailed process. So the objective of this project really was to reduce energy through the effective use of sustainable solutions and to reduce the environmental impact of the building. And at the time there was a bespoke BREEAM requirement for very good. The first part of it was the solar shading analysis, and it was really to investigate the building in the context of surrounding buildings and the park behind it. The ivy gardens, the architectural intent was to sort of bring the outside in by involving the ivy gardens and the building. So obviously you don't want to have an imposing shading on an area that you're trying to incorporate into the whole scheme. It also helped us to look at maximising winter solar gains to reduce the heating load, maximising in certain areas the winter lighting load or daylight availability to reduce the lighting load. And in addition, we looked at various shading options for it. Apart from a stepped facade, there's also a solid section on the south and southwest facades. And then we looked at a few different iterations of fixed shading on the east, west and south facades. This in turn is linked into dynamic simulation, and it gives, rather than using generic data for solar gains, it will actually bring that shading analysis into it. So you'll see the effect, the reduction of solar gains over the day, according to the sun position. The second part of it was, and this was really concerned with the dispersal of exhaust from CHP and boiler flues, which it's a wind wake study. It's essentially an external CFD, as you can see above here, which looks at the airflow around the building's footprint. And this was done using virtual wind software, which is a large eddy simulation software. And it uses a fairly basic mass model to represent the geometry of the building without going into too much detail on it. As you can see here, this is another version of it, but it was mostly to optimize the location of air intakes, because obviously you don't want the exhaust from CHP and boiler plant getting entrained in the air intakes, which, because of the nature of the building and the high occupancy, there was quite a lot of ventilation strategy required for it. In order to assess the natural ventilation, we set up a natural ventilation bulk airflow model, which it's a module within IES. The top here is just a sketch scheme of one of the ventilation strategies. On the bottom you can see the ventilation rate over an entire year. So you can look at that at 1 minute intervals or any particular day. One of the good things, or one of the things that we really like about MacroFlow is that it allows you to model control strategies with a high degree of accuracy. So whether it's based on external and internal variables, carbon concentration, wind speed, whatever you like, you have the control to model that. And again, this is linked into the thermal simulation. It helps to analyse overheating and occupant comfort and the effectiveness of thermal mass and light cooling, which in the area, particularly of climate change adaptation at the moment, and the question of whether we can adapt our buildings to climate change, which is a whole other story. This is particularly useful in that area as well. And in turn, after the thermal analysis, we were able to feed this into modelling various sustainable sources of energy, both individually and as a mix, and in turn feeding that into life cycle costing. So you can pick up the optimum strategy in terms not only of energy use and cost, but carbon emissions. Okay, I'm going to just mention a few words about CFD because it's been used quite a bit on project analysis. It's a method of simulating fluid flow and heat transfer processes in a space. It takes into account climate, internal gains from people, equipment, etc., and HVAC systems. So you can pretty accurately visualize airflow patterns, heat transfer from people and equipment, etc. And again, in the area of climate change adaptation, this is becoming a big issue with use of low energy equipment, effective use of thermal mass as well to mitigate the radiant component of the heat gains. It's not always possible to reduce the entire heat gain in a building, but you can push sections of it forward, and that way you reduce the coincident solar or the coincident heat gain at a particular time in the day. So the actual peak cooling load might not be reduced, but the duration of time over which it occurs can be. This example is from one of the auditoria unit, and it's where CFD was used in this project as well. There was 3 auditoria with various occupancy from 3,700 people down to 550 in the foyer, and a few different ones in between. It was really used to model air change effectiveness at the top. So you can see hotspots, areas of stagnant air, etc. And again, in this particular case, it was modeled winter, summer, all the possible occupancy times, different seating arrangements to get the optimum solution for the project. This is an example of the output. So you can see the temperature contour rising with buoyancy. And this is very important, particularly when you're designing stack ventilation, and you want to effectively use that buoyancy to let the air rise and exhaust, bring in cool air at a lower level. This is just another example, for comparison's sake, of where it can be used. This was done by our Australian colleagues on the Sydney Opera House, which is part of their continuing brief. They've been involved there, I believe, since it was built. And this was analysis of the main auditorium of it. The intent of the ventilation strategy was to bring low velocity external air from under the seats, let it cascade down along the tiers, so then in turn that would prevent the warm air from the main space rising under those levels and becoming trapped and causing hotspots, making the occupants uncomfortable. And again, areas of stagnant air are considered as well. They did a large number of different iterations on this until they got the preferred solution for it. The other image is just a sketch design of the design intent. So it's just an example of where this can be used. We've been looking at Vasari for early stage BIM or early stage design, early stage analysis, and what it can do for us. We use a very basic mass model, which reduces the modeling time, and in effect, at this stage, you really only need a mass model for some of the analysis. It gives a quick response as well, in that you don't spend a lot of time exporting results to Excel to Word, writing up reports. You literally click a few buttons, within a few seconds or a few minutes, you get a PDF back with your graphs and your charts, and it's very easy to compare the results from it. It brings in some of the features of Ecotech, such as that should be actually sun path rather than solar shading, solar radiation and wind tunnel. At the moment it's a beta version, but it is being updated pretty much every few months based on user feedback, which is really the best way to get feedback on something like this. Put it in front of someone, let them break it and put it back together again, and then tell you what's wrong with it. The 3 Ecotech features on it, and these are actually quite good. The solar radiation component, it gives an early indication for optimizing glazing ratios and locations. The possibility of different radiation levels on different facades, and this can be done very quickly. Some part is very similar to one I showed earlier on with the National Concert Hall project, and it can give you an indication of overshading right-to-light issues or possible right-to-light issues with other buildings. And the wind tunnel, which looks at wind wake and tunneling and identifies implications for pedestrian comfort. Now, this is particularly of use in tall buildings and high-rises. But what I really like about this is, okay, you can't export a movie file from it at the moment, but if you look back at the early stages of the National Concert Hall project, where there was a huge amount of time, expense and modelling went into doing things that you could literally probably do with the press of a button at the moment. And in simulation, for the length of time I've been at it, it's one question which keeps popping up. Someone wants you to look at a design strategy and to go, can you not just press a button and get an answer? And unfortunately, to date, that hasn't been the case. In terms of climate analysis, Vasari uses various climate metrics, such as the windrows up here, which can be quite useful in looking at the prevailing wind direction, wind frequency, wind speeds, and the location of ventilation exhausts. Like, for example, atria and stack ventilation, where you need to have it in the negative pressure zone. So depending on this is site specific, so you can see exactly what's going to happen in terms of wind speed, direction for that site. And also the temperature swing during the day or between day and night, which is very useful for establishing the effectiveness of thermal mass at night cooling. The comparative energy analysis as well, it's a quick way of checking the implications of various design strategies, whether it's fabric or services. And it gives, they are pretty rough results. It's monthly outputs rather than every minute or every few minutes. So there is really an accuracy, probably, I've heard plus or minus 20%. Now whether that's correct or not, I'm not 100% sure. But it can give an early indication of the implication of design strategies or design options. And see basically if the design is moving in the right direction. It'll direct further analysis down the line. So the objectives of using BIM-based analysis is basically to influence the design at an early stage and direct it get it moving in the right direction. It saves a lot of time in simulation work. It also helps identify areas where you can validate your design at a later stage in dynamic simulation. And because it's inclusive, it promotes team working. I think the inclusive element of it is very important because to date with building simulation, because of the amount of training and experience required, it has been largely confined to specialists. So you have a design team sitting around looking at options, they send it off to a simulation specialist, he'll run all the analysis, write a report, send it back to them. They read the report and probably take his word for it, or hopefully take his word for it. But with this, everyone can get involved. You can look at various design options, you click a button and you can actually see, it's like I see, therefore I believe. So you can actually see what the implications of your design options are. The limitations, and it is in terms of accuracy, is that it's generic inputs and indicative outputs. But at this stage of design, that's probably all you need. You don't need that huge level of detail. So it leads to being, it's ideal for concept stage. So the impact of building performance, it's an easy method to evaluate different design options. To some extent, it would eliminate the necessity to import and export models between different softwares, which has its own issues. And it's a cost-effective method of integrating between BIM and DSM. This is a comparison of, I suppose, our traditional workflow and what we'd hope to achieve by using this software. Traditionally, you're waiting on hopefully developed and frozen architect's drawings, which doesn't always happen. Then you go into building a model, inputting all that data, control strategies, internal gains, everything else. Once you get to that stage, the design might actually change, and then you're back to square one. Or you can move on to preliminary analysis, run your iterations on that, confirm results, move on to detailed analysis. Something again might change, you're back to square one again, and eventually you get to your output. But if you can use the mass model at the very earliest stages, then use BIM analysis and have a seamless transfer into detailed design, it really speeds up the whole process. You can do your iterations quickly in BIM rather than in DSM, where you're going to waste a huge amount of time and effort and money trying to get the design right. The facility for exporting from BIM to IES is, the one I'm familiar with is GBXML. And it's specifically developed to transfer information between BIM and engineering and analysis tools. One of the issues I've found with it, and I believe from talking to Ralph and Pat that this is actually improving, but the requirements from the architect's model are completely different to the requirements from an energy model. The architect wants to visualize the building, have a lot of parametric data attached to it at an early stage to inform the client, to inform costing and scheduling. The energy model is basically a mathematical model, so it needs the least amount of information to solve a mathematical problem. So you're really just looking at thermal properties, volumes, the correct places of glazing, etc. As I said, I believe it's improving. It's not completely seamless yet. And it's not particularly because of GBXML. I think it's just that dynamic simulation software and BIM software are both very well advanced and very good at what to do individually. But the weakest link is the actual integration of both of them to make it seamless. So, desirable aspects of project deliverables. As I said, the issue of accuracy or the required accuracy at certain levels of the project. And a flexible design solution demands that you agree basically at concept stage, right, we don't need 100% accuracy in this. We can deal with a 20% margin, and we can then input that into costing, scheduling, and get the project moving in the right direction. And then later on, we can deal with reducing that margin, getting it down to 5% or whatever, and looking at specific areas of it. Okay, building regulations, which has its own issues in terms of verifying energy compliance or energy analysis. Dynamic simulation modelling can be used for it, and it's a lot more accurate. The issue is, in Ireland at least, only SBIM is accredited to be used. Now, SBIM is basically a steady state calculation. I wouldn't call it a spreadsheet, but it's not far from it. Using monthly average data. And in the UK, they're talking about discontinuing the use of dynamic simulation for this. I don't know whether that'll happen or not, but I don't think it would be a good step, because if we're going to look at a building's energy consumption, the one thing we need is accurate data. We don't need assumptions and what is and isn't included in it. We're basically looking at fabric, services, fixed occupancy errors. If you look at medical facilities, for example, the amount of energy used and consumed in medical equipment, and even such things like lifts, ICT equipment, it's far outstrips what you're going to use probably in your building services. Carbon Buzz, which is it's a collaboration between CIBSI and Riva. It's an industry-wide initiative, and the purpose of it is to aid engineers and architects to close the performance gap between actual and predicted energy use. And the target is to build an evidence base for low energy solutions. This graph basically shows, from their typical data, the energy gap or the performance gap is typically between 150 and 200%, which is very worrying. As I mentioned, the simplification of models. If you're using SBIM, which is not far from an Excel operation, you're building a lot of assumptions and defaults into your calculation. During the design process itself, the building's going to change, or the design intent will change as it goes along. The fabric, services, controls, etc. But the biggest factor in this is probably the uncertainties associated with occupant behaviour. Because people won't leave thermostats alone, they'll tweak with it, they'll leave lights on. You might have people working late or whatever, and then commissioning of controls so they don't drift. These all add to the problem. So a possible solution is to use, as I said, accurate evaluation of energy is very important. We need to know, if we're going to save energy, we need to know what energy the building is actually using. So the possibility, and a scenario where perhaps BIM and dynamic simulation can work together, is using that stripped back energy model for handover at 7D stage. And using the high degree of accuracy that DSM gives us to feed into that for facilities management. And in turn, over the entire life cycle of the building, this can inform energy strategies, investment strategies, and life cycle costing. The final, I suppose, conclusion of it is that there are areas where both software are very, very strong, but they're not necessarily suited to all stages of the design process. BIM is very suited, or BIM-based analysis is very suited to early stage design. because you have that quick reporting, and because you can get the whole design team involved in it, you're not waiting for a specialist to issue a report. The design process doesn't really allow, or is not suited to dynamic simulation modeling being used at early stage. It just delays project deliverables, it pushes everything down the line, it adds to the costs, and at that stage of the project, there are low value returns from it. But I think where DSM comes in really handy is fine-tuning, testing and validation. And if we can get to a stage where in the design process we can use both types of software to their individual strengths in a collaborative way, it'll move us a long way down the line. And I said a possible solution in the 70 BIM energy model is the combination of both types of analysis. I know there is a certain amount of development going on being able to link in real-time BMS data into a dynamic simulation model. That could be a year or two down the line. There's a European funded project looking at it at the moment. So if that progresses and you can link BMS data into a dynamic simulation model and perhaps link that into the BIM energy model, it'll go a long way to reducing our carbon footprints, the impact on the environment, and reducing costs overall. Thank you.